Welcome to New York City Atheists, live on tape, brought to you by New York City Atheists Incorporated. I'm your host, Dennis Horvitz, the David Letterman of the Hopelessly Damned. Today we're going to try to answer a few questions, or at least explore them. Is there life elsewhere in our universe? Sure, if you get there on a Saturday night. But, look, I do this for free, okay? I'm doing this from one of our notorious Sunday brunches, New York City Atheist Sunday brunches. In any case, we're going to try to explore today questions such as how do we define life? What conditions are required for it? Where in our galaxy could life other than on Earth be? Are there other intelligent beings? Are they on their way? We should probably cue the spooky space music right now, but we don't want to pay the royalties. In any case, to answer this question and related questions, our blank speaker today is Dr. Fred Walter. He is from Berkeley, California, and he is now a professor of astronomy at the Department of Physics and in astronomy at Stony Brook. And in addition to some of the aspects of astronomy and biology, some of the topics perhaps that we will touch upon today is, first of all, the physical conditions of the universe as it exists now, and from the age of the Earth. I'm sure that we'll probably get into the young and old Earth creationism and during our question and answer period. And the Drake equation, which is, I guess, the best means so far by which scientists have to estimate the possibility of extraterrestrial life. And I guess that would be intelligent, also including intelligent life elsewhere in the universe. And the information theory. How would we recognize signals from intelligent life on other planets? Well, if they call collect, that would be one way. But in any case, I'm not the one that's going to be answering this question, so it gives me great pleasure to introduce Dr. Fred Walter.
Thank you. I didn't say when I was signed on I was going to give you the answers. I said I would ask the questions. When in doubt, the answer is 42. What we're going to talk about, what I'd like to give you is an overview of a whole bunch of questions concerning this very important question of life in the universe. What do we mean by life? Will we know it when we see it? What can we do about it? We get into all sorts of tangential issues. What's out there in the universe? Feel free to ask questions if I don't cover anything. Be warned, though, a couple of things. One, I'm an astronomer. I can answer questions. I know about the astronomy and the physics. I don't know much about the biology and chemistry, but I teach this stuff. So what you're getting is the less than 1 hour version of an entire class. So if you ask too many questions, this could go on until Tuesday. The popular view of life in the universe is given by this book cover. Many of you probably read some science fiction, and we read about the little green men who are being downtrodden there by John Carter, who went to Mars to rescue the princess. That's not what we think life in the universe is like, if there is indeed life in the universe. So we're going to start by talking about life. What is life? What do we mean by life? With the caveat that this is life as we know it. We have examples, a plethora of examples on the Earth of what a living thing is, but who says that that's all there is to it? I mean, it could be something completely different that we wouldn't recognize. So we're going to talk about life as we know it to start with. So what are the properties of something that we would consider to be alive? Well, the first thing is it produces order out of disorder. The natural state of the universe is one of disorder. We'll get to that in the next slide. Something that's living is something that can reproduce itself. Evolution is reproduction with errors. Things can change. It grows, it develops. It doesn't start fully grown. It generally starts small and gets big, or at least it changes in some respect. Living things utilize energy. Well, that comes out of item 1 here. In order to produce order out of disorder, you need to utilize energy. It responds to its environment. It has to live in some type of environment, and it must get resources out of the environment, it must respond to the environment, there must be reactions to stimuli, and finally it adapts and evolves, it changes. Something that does not change, well, it's not going to live for very long because the universe is changing around it. So that's what, those are sort of, and it's not all inclusive. You can think of different things you would want to put in there, but those are some basic things of something that's alive has to satisfy. We're up against the universe. The universe is fighting back, it's antithetical to something living, in a sense. The laws of thermodynamics are quite strict. The main one is that energy, or the main one is the second law. But what the laws of thermodynamics say is that energy cannot be created. Law of conservation of energy. You can transform energy, you can turn heat into light, and vice versa, but you can never create or destroy energy. In a closed system, entropy always increases. Entropy is the measure of the disorder of the system, the number of states that a body with an ensemble of many bodies are in. It's very unnatural to be ordered. It's much more natural to be disordered. Life requires order. Life organizes. So we're fighting the second law of thermodynamics. And that means it takes an input of energy. You will see people saying that the development of life requires divine intervention because they don't understand the laws of thermodynamics. In fact, they understand the second. They know that order requires energy, but they know that entropy must increase. The key word is in a closed system, or the key phrase. In a closed system, entropy must increase. The universe is the only closed system we have. So anytime you create order on the planet Earth, you're more than offsetting it by disorder in the sun, where the sun is increasing its entropy because it's burning hydrogen into helium and producing light and energy in the process. So in the Earth-Sun system, entropy is increasing, while on Earth it's decreasing. So you have to understand all three laws of thermodynamics, not just one, in order to make a scientifically valid case. The third law is interesting but not terribly relevant. It just says you can't turn anything off. You cannot reach absolute zero. So that's sort of a definition of what we're looking for in life. What's alive? I mean, how will we know when something is alive? Well, we know it when we see it. I suppose you could create your own living thing, like they are doing in this movie. That, of course, is the original Frankenstein. So we're going to talk about four different meanings of life. There are four possible definitions. There are actually many more than four possible definitions. These are just four that encompass most possibilities. The first is a thermodynamic definition of life. Thermodynamic meaning you're producing order. You're violating, apparently, the second law of thermodynamics. How do you produce order? You have to overcome entropy. Well, something in nature that overcomes entropy and creates order out of disorder is a crystal. Those crystals are nicely organized. That's a quartz crystal. There's no question that this is more organized than just little particles of sand floating around someplace, settling down someplace. So, is a crystal alive? Most people would say no. There are New Agers who might say that crystals are alive. Crystals are not alive. Nonetheless, they do satisfy a thermodynamic definition of life because they do create order out of disorder. There is a metabolic definition of life. It metabolizes, it uses energy. It produces a different kind of energy, transforms energy via chemical reactions. Something that does that you all know is fire. Fire is oxidation. It converts something into something else. It produces heat and light in the process. That's a metabolism. In a sense, we are, as oxygen breathers, as aerobic organisms, we have fire in ourselves. We're undergoing oxidation, in a sense. So there's a metabolism involved here. But is fire alive? Maybe certain animals would say yes, but most people would say fire is not a living thing. But it's a metabolic definition. This metabolic definition, something producing energy, is again necessary but not sufficient for something to be alive. Then there's a biochemical definition. A biochemical definition starts getting to something that's pretty much specific to life as we know it. A biochemical definition of life involves using specific enzymes, specific reactions, again, to do chemistry. You're converting this into that, you're releasing energy in the process, you're converting adenosine triphosphate or sugars into adenosine triphosphate, which stores energy, and then you can release it later. And it uses specific chemical reactions. That picture is a drawing of a protein, a rather complex protein. Biochemical definitions of life are, as I said, specific to life as we know it, life on Earth that we've been able to examine. There may be other kinds of biochemistry in the universe, we just don't know what it is. But this is a very specific meaning of life. If something undergoes certain biochemical reactions, maybe it's alive. On the other hand, we can have biochemical reactions happening in the laboratory in things that are clearly not alive, at least not yet. We haven't been able to create something that is, we think, living in the universe. And then finally, there's the Darwinian view, as you can sort of see going on in the movie, where life is self-sustaining, reproducing, and is capable of evolving. And all evolution is reproduction with errors. Okay? If you have something that reproduces perfectly every time, it never changes, and as I said, you have to adapt. Life has to adapt because the universe is continually changing. Just as an example, the sun is today 70% more luminous than it was 4 billion years ago. The Earth is warmer than it was 4 billion years ago, on average. And actually, during the last 4 billion years, the Earth has gotten warmer and colder, and things that haven't adapted, haven't evolved, aren't with us anymore. So there's a Darwinian view of life as self-sustaining, reproducing, and changing. So that's what we're talking about in terms of things that are alive, things that are living. We're looking for things that satisfy those properties, with the same caveat that that's life as we know it. There may be different definitions. You may have some of your own, but that's sort of what you look for what you know. You don't look for what you don't know, because you might not recognize it. So, talking briefly about life on Earth, it's the only example we have of life. And when we ask the question, what's life going to look like elsewhere in the universe? Well, Earth is the only benchmark we have. It's the only example we have that we can look at. So, let's try to understand life on Earth. Life on Earth is complex. Life on Earth has been around for 3.8 billion years. It evolved fairly quickly. It started up very quickly. The Earth is, as you should know, 4.6 billion years old. The Sun is the same age. The Earth's surface was pretty much molten until about 4 billion years ago. It may have been solid before then, but it collided with an object about the size of Mars, and the result of that collision was the Moon. That's 4.5 billion years ago. And that remelted the Earth's surface, and the Earth was pretty much inhospitable if you have a molten surface. I mean, I don't know of any living things that can live in lava. There may be something, but I don't know what it is. So the earliest evidence we have for life on Earth is a biochemical residue. It's basically the carbon-13 to carbon-12 ratio. Carbon comes in a number of isotopes. Carbon-13 has all carbon atoms have 6 protons. Carbon-13 has 7 neutrons. Carbon-12 has 6 neutrons. Carbon-13 is heavier than carbon-12. Therefore, it moves around more slowly in solution. You have water, you have carbon, molecules involved in carbon. The ones that have carbon-13 are heavier. They move less quickly. They are less likely to take part in chemical reactions. And it's a fact that living processes on Earth concentrate the lighter isotope carbon-12. So you look at a bunch of carbon, some soot, some whatever, in this rock. You find them in rocks 3.8 billion years old. You measure the carbon-12 to carbon-13 ratio. It's more like things that are alive or were alive than inorganic processes, which have the same ratio you have in the universe as a whole. So this is very tenuous evidence that there were biochemical processes happening on the Earth 3.8 billion years ago. Half a billion years or so after the Earth's surface solidified, these found in the oldest rocks that we have been able to find on the surface of the Earth. Unfortunately, the Earth is not a museum that saves everything for us. We have to go and look, and the oldest rocks have been subsumed into the mantle and reprocessed and melted. So the oldest rocks are, well, about 3.8 billion years old, and they have evidence of what might be something alive. So life got going very early after the Earth was formed. That's something to keep in mind. There was no great roadblock to life forming on the Earth. It happened quickly. If it happened quickly on the Earth, maybe it happens quickly any place that there is the right conditions occur. And the conditions on Earth 3.8 billion years ago were not like they are today. The atmosphere was highly corrosive. It was reducing. It was hydrogen and carbon dioxide and ammonia, methane. There was no oxygen. The sun was 70% as much solar input. It was on average cooler. Of course, the atmosphere was a greenhouse atmosphere, so it trapped heat. So it kept water was liquid, but much of the surface was covered with volcanic activity and all that. So it's a very different place than we have today. Anyways, it arose under these adverse conditions. It arose very quickly, and it evolved fairly rapidly, because 300 million years after we have this first biochemical evidence for life on Earth, we have what look like essentially modern fossils. They're algae, they're stromatolites. Like you can find today down in Australia, there are fossils that look exactly like modern stromatolites 3.5 billion years ago. So life has been around for a long time on this planet, at least 3.5 billion years, maybe 3.8, maybe more. When you think of life on Earth, this is what you think of. The vast savannas of Africa, the meadows of the American West, and plants and big animals and things like that. This is not the norm. You would not have seen this 500 million years ago on this planet. In fact, this is not representative of most of the life on the planet today. What is representative of life on the planet back then and today is situations like this. These are called black smokers. These are volcanic vents at the Mid-Atlantic Ridge, a mile or so beneath the surface. There is no sunlight here. There's a lot of living things here. They're microscopic. They're unicellular. You don't see them. But you're in a place where you have liquid water. The temperature goes from basically boiling temperatures right at those vents. Right about here, the temperature is boiling, and right out here, the temperature is about 32 degrees Fahrenheit, because it's pretty cold down there, and very high pressure too. You've got no sunlight, no photosynthesis. What do these things live on? They metabolize hydrogen and sulfide, they metabolize iron sulfide, they metabolize sulfur. They live just fine. And we think some of the earliest life on Earth was probably like this. And it's still doing well today. Life shows up in lots of other types of extreme environments on the Earth. Every place we've looked on the surface of this planet, we found living things. From 4 miles down below the Earth's surface in bedrock, in cracks in the rock, you find bacteria. They're called lithophiles. They live in igneous rock. They live very slowly. There's not a lot of stuff for them to live off of, but they're alive. They're clearly bacteria. And you go up in the atmosphere. You can go up some tens of kilometers, and you will find bacteria floating up there, living on dust grains. Maybe they just lifted up by storms. I don't know, but you can find them up there. They probably don't live there permanently. But you find bacteria and archaea, which is a more all-encompassing term, that live in the hot springs, the geysers in Yellowstone Park, where the temperatures approach 100 degrees Celsius. Things that would parboil you instantaneously. There are thermophiles that are quite happy to live there. They thrive there. Thanagens, which are anaerobes, they don't use oxygen. They live off of methane. In fact, most life on this planet does not use oxygen. Oxygen is highly reactive. Oxygen is poisonous to most life. It's not probably the case that life cannot get started in
oxidizing environment. In fact, there was no oxygen on this planet until about 2 billion years ago, 2-point-something billion years ago. It is basically waste product from green algae, and they caused one of the first big ecological catastrophes on the planet by basically poisoning the atmosphere, by putting oxygen in the atmosphere, which poisoned most of the living things until certain bacteria learned to live off of oxygen, or somehow protect themselves against oxygen. Acidophiles live in highly acidic water, pH greater than 1, that's stronger than lemon juice. Halophiles live in highly saline environments. You find things living in the Dead Sea, in the Great Salt Lake, etc., where there's basically well, most large animals, us included, could not live. The important lesson here is that wherever we look on the Earth, we find living things. And any environment that you can find on the Earth, from the driest deserts to the coldest to the hottest to the whatever, you will find something that is adapted to it. And that tells you that when you go look for life in the universe, don't look for something that looks like Nebraska. Look for something, well, you take what you can get and you look for life there, because if life elsewhere is like life on Earth, it's going to be there. And it will have adapted to whatever the local conditions are. That, of course, makes it more difficult to look for life, because, well, it's probably not going to be big cats walking over the plains. So that's life on Earth. How about life elsewhere? Again, we don't know. All we know about life is life on Earth, and maybe life elsewhere is different. I like this quote from Jean Giraudoux, the Mad Woman of Chaillot, where the Mad Woman is speaking, and she says, "Are you so stupid to think that just because we're alone here, there's nobody else in this room? Do you consider us so boring or repulsive that of all the millions of beings, imaginary or otherwise, who are prowling around in space looking for little company, there is not one who might possibly enjoy spending a moment with us? On the contrary, my dear, my house is full of guests." Well, I won't go so far as to say that space aliens are in this room with us today, but keep in mind that the universe is big, and there are lots of opportunities for life to get going, and maybe there is something else out there. So, to do astrobiology, you have to ask the right question. A lot of science is asking the right question. It's not, getting the answer is not all that important. We don't know what the right answer is. You want to get an answer, but it's the question that's important. So, what are we looking for? That's the question in astrobiology, and how will we know when we found it? Okay, we know what life, as we know it, is like. Lives on water, requires liquid water and all that, but there is also the possibility for life as we don't know it. We know what environments work on the Earth, any environment that supports liquid water. What environments could life as we don't know it entail? Again, we don't know. Science fiction writers are probably not ingenious enough to come up with all the locales. Maybe some of you are, but it's a question. Where is life? And we'll know it when we find it. So now we get away from biology and the chemistry part of the talk into the astronomy part. Solar system. What are the locales in the solar system where life might exist, other than the Earth, of course, where life does exist? And what constitutes evidence? How will we know it when we find it? Well, evidence of life could consist of a large multicellular object walking in front of your camera. That would be too easy. Probably not going to happen. So, evidence will probably consist of, well, that's the images of bodies there, but we're most likely to see cells or fossils. Okay? Most living things on this planet are, most species are dead, most things are fossilized. That's probably true elsewhere as well. So we have to find fossils or cells. Those are hard to see. You need microscopes. You need to dig. They don't just walk across the field of view. So it's going to be hard to find it. Artifacts. Maybe there are artifacts out there that we can recognize. You know, the pyramid, something like the Great Pyramids of Egypt on another planet, that might be good evidence for life out there. Maybe a real flying saucer, if anybody actually got evidence the UFO people like to say that it's being visited, but they've never produced any evidence of it. So if you could actually have an artifact, that would be very strong evidence that there's something out there. Another one is non-equilibrium conditions. Life is a non-equilibrium process, because anything that violates the second law of thermodynamics locally is non-equilibrium. You are going against the laws of thermodynamics. You're turning a disordered state into an ordered state. These three spectra on the right, these are plots of basically intensity versus wavelength for the atmospheres of 3 planets. But this is Mars, this is the Earth, this is Venus. And this is if you take a telescope, put a grating or a prism in front of the spectrograph, disperse the light into its colors. This is the infrared. You don't need to know what the wavelength is. The brightness is up here, and here's an absorption line due to carbon dioxide. There's carbon dioxide in the atmosphere of Venus, the Earth, and Mars. If you look at the atmosphere of the Earth, which actually means you're looking at the atmosphere, you're looking at the moon, the Earth light is reflected off the moon. What you see that you don't see on Mars and Venus is you see water in the Earth. Well, that's okay. Earth is just the right temperature. Venus is dry, and Mars is pretty dry too. Earth is humid. It's got water. That's not a non-equilibrium thing. Water is actually quite abundant in the universe. What you see in the Earth is ozone. Ozone is a non-equilibrium product. Ozone is created by, of course, ultraviolet reactions of breaking down other more complex molecules, but it implies that there must be some non-equilibrium chemistry going on in the Earth's atmosphere or on the Earth's surface, generating these gases that break down into ozone.